buffer test. Here we go. The first one, questions 1 through 4, asked you to answer certain things about different buffer solutions, or maybe just a solution in general. So like this first one says a solution with lowest pH. Well, lowest pH is going to be given to us by an acid, and the especially lowest pHs will come from strong acids. So hopefully you have your 7 strong acids memorized, and we're going to come up to our answer choices and find one that hopefully has a strong acid. Well, that's a base. That's a weak acid. That's the conjugate base of our weak acid. So first, A and B are out. HCl, there's a strong acid, so I'm thinking C is going to be looking pretty good. NaOH is a strong base, so D's out. And then E is a weak base and a weak acid. And so they're probably going to cancel each other out and have a pretty neutral pH. So the only one that had a low or a strong acid for a low pH is going to be letter C. So that's going to be our answer choice there. Then most nearly neutral. As I was going through these, I mentioned that this was a weak base and a weak acid. So it's going to be really close to neutral. So E goes here. Then we have a buffer with a pH of greater than 8. So we want to look for, since we want a greater than 8 buffer, we want to look for a weak base with the conjugate acid of that weak base. And if we come back up here, you see NH3 is a weak base. NH4Cl is the salt containing the conjugate acid of that weak base. So here is our basic buffer, basically. Haha, not funny. And then a buffer with a pH of less than 6, we want to look for a weak acid and a salt containing the conjugate base of that weak acid, and that would just so happen to be right here. We have H3PO4, phosphoric acid. The conjugate base of H3PO4 is right here with this H2PO4, and so weak acid, conjugate base of weak acid, gives us a pH, or a buffer with a pH of less than 6, a slightly acidic buffer, so B goes there. Now, scrolling down to the next set, looking at what we have, solution with a pH less than 7 but not a buffer, buffer solution with a low pH, an acidic buffer, and then we have C as a basic buffer, D is just a basic solution that's not a buffer, and then E is a neutral solution. And they gave us some ionization constants. Keep in mind, on the multiple choice, you don't have a calculator. So you won't really have to use any of these unless you just so happen to forget that, acetic acid is an acid, as evidenced by its Ka, or that ammonia is a base, as evidenced by its basic, this is its Kb. And then this is carbonic acid, and it has 2 K values for each of the 2 hydrogens. Solution prepared to be initially 1 molar NaCl and 1 molar HCl. Well, we have a neutral salt and a strong acid. So that would be a solution with a pH less than 7, and it's not a buffer solution because you can't have a buffer made out of a neutral salt and a strong acid, so this is going to be A. So, oh crap, what did I just do? Sorry. A solution prepared to be initially 1 molar Na2CO3 and 1 molar CH3. Let's see, we've got sodium carbonate and sodium acetate. Now this carbonate is a conjugate base. The acetate ion is a conjugate base. But since these guys don't have any kind of common, yes, they have the sodium in common, but sodium is a neutral ion, so it's not going to contribute to a buffer. But since these two don't have any acidic basic ions in common, we're not going to have a buffer. And since they're both conjugate bases, we are going to have a solution, pH greater than 7, because it's basic, they're conjugate bases, but it's not a buffer solution. So that's going to be D. And then we've got 0.5 molar acetic acid and 1 molar sodium acetate. We see here, acetic acid is a weak acid. Sodium acetate, the acetate ion, is the conjugate base of acetic acid, so we have a buffer. And since acetic acid is a weak acid, we have a buffer with a pH of just less than 7, or B. So that goes there. Scrolling on down to our last question. On the basis of the information above, a buffer with a pH equal to 9. So we're looking for a basic buffer can be made by using. Well, first of all, let's look at these answer choices and cancel out the ones that aren't even buffers. So if you look at this, pure sodium dihydrogen phosphate, that's not a buffer. So that's out. So you can cross that one out. If I could cross it out, I would, but I can't. Then we have, maybe I can just like color it, and then it'll be, there we go. Oh, didn't mean to color that one. Then we're going to look at this one. We have phosphoric acid plus the dihydrogen phosphate ion, which this is an acid, this is its conjugate base. But if you come up here and look at the Ka for H3PO4, this is a buffer, so we would hang on to it, but hopefully you recognize this as an acidic buffer. And we want a basic buffer, so that guy's out. Then we have this guy. We have dihydrogen phosphate ion, which has a Ka of 8 times 10 negative 8. Well, that 8 is really close to that 9, so I'm liking that. And then the other part of it is just the phosphate ion. Well, this is not the conjugate base of this guy. And so that is not the correct answer. Then coming on to D. We've got the dihydrogen phosphate, which is what we want. And we have the hydrogen phosphate, which is the conjugate base of, or I guess it's really kind of the conjugate acid of this guy, because this guy is more basic than acidic. And so this will have a pH of about 9 because the H2PO4 has a Ka of 8 times 10 to the negative 8. Remember, it's this little exponent right here that really gives you a hint as to what the pH is going to be. And so 8, really close to 9. So I'm liking D. And then just to look at E, just to double check it, we have hydrogen phosphate and phosphate. So this is a base conjugate acid combination, but the Ka for HPO4 is 5 times 10 to the negative 13. So this is going to be a pretty basic solution. pH probably in the range of 13, 12 to 14, somewhere in there. So that's pH is too high. So our correct answer is going to be this one. So that was all for the multiple choice. Now we're going to move on to the free response questions. There were 2 of them, and here's the first one. Oops. Okay. Dang it. Open up. So the first one says, you got ionization constant, Ka for propanoic acid, right there, is 1.3 times 10 to the negative 5. I'm going to write that out because I know that's kind of hard to read. 1.3 times 10 to the negative 5. Calculate the hydrogen ion concentration in 0.2 molar solution of propanoic acid. Well, if you remember, the Ka of any weak acid is going to be equal to x squared over the initial concentration of your acid, where x is equal to the hydrogen ion concentration and also equal to the conjugate base concentration, which in this case is C2H5COO minus. So, plug this stuff in. 1.3 E negative 5 equals x squared over our starting concentration of our acid was 0.2. Rearrange this, you get x squared equals 2.6 E negative 6, therefore x, which equals that hydrogen ion concentration, is equal to 0.00161 molar. So that's A. B, calculate the percentage of propanoic acid molecules that are ionized. Well, if this is how much hydrogen ions we have, if we want to know what percentage of it has ionized, we take this amount that's ionized, divide it by the amount that we started with. Let me label this as A, switch colors to do B. So we take the amount that is actually ionized, because remember, this is also equal to the propanoate ion, which is, wait, I got ahead of myself. Calculate the percentage of propanoic acid molecules that are ionized. So we're going to take the propanoic acid that we started with, the 0.2 molar, and the part that's ionized is this 0.00161 molar. And of course, to make it a percentage, you multiply it by 100. And you end up with 0.81%. Switch colors again. C. What's the ratio of the concentration of the propanoate ion to that of the propanoic acid in a buffer solution with a pH of 5.2? Well, we know we have a buffer because we have propanoate ion and the propanoic acid together, which means it's a buffer. And so we get to use pH equals pKa plus the log of the base, C2H5COO minus, over the acid. And if you look, there's our ratio right there. This is the ratio of propanoate to propanoic acid. So all we have to do is rearrange this and treat this whole thing right here as one big giant X. So our pH, they told us, is 5.2. Our pKa is going to be the negative log of the Ka. So negative log of 1.3 times 10 to the negative 5 works out to 4.89. Plus the log of, I'm just going to go ahead and call this X. So rearrange this stuff and you end up with 0.31 equals log, oh crap, I'm doing that connecting thing again. Equals the log of X, therefore X is equal to, it's like 2.06, which basically say 2, so you have a ratio of 2 to 1. So there's your ratio. And then D, last but not least, move this down so y'all can see what's going on. Let's do some red. 100 ml sample, different buffer solution, propanoic acid is 0.35 molar, sodium propanoate concentration is 0.5 molar. To this buffer solution, that much solid NaOH is added. Calculate the pH. Well, we have our buffer, and then we added sodium hydroxide to it. So that means we had a reaction occur. So I actually am going to erase this whole bottom part because this is going to take me some room. Oh, I don't want to delete that. Sorry. Okay, so we're just going to leave that there because I can't erase it without erasing the other question. All right, so our equation is going to be the reaction of the solid sodium hydroxide, and because this is a base, it's going to react with the acid. So I'm going to take my acid, C2H5COOH, and I'm going to add to it the sodium hydroxide. But remember, sodium is a neutral ion, so all I care about is the hydroxide. And I'm going to produce the propanoate ion. And this hydrogen is going to go with that hydroxide, and we're going to make some water. Now, my starting concentrations, it says that I have, my propanoic acid is right here, 0.35 molar. And my sodium propanoate, the propanoate ion, because remember sodium's a neutral ion, I don't really care about him, is 0.5 molar. And we added 0.004 moles. These are in molar. This is in moles. So we're going to have to get everything into moles to be able to deal with this. Well, we have 0.1 liters. 100 milliliter is equal to 0.1 liters. So I got 0.1 liters here. 0.1 liters here. So this works out to a molar, not molar. This works out to 0.035 moles. Let's do it again. It's very frustrating when it does that. And this works out to 0.050 moles. Well, the hydroxide, we have 0.004 moles. So since everything is a 1-to-1 mole ratio, and this is what we have the smallest amount of, the hydroxide is going to be our limiting reactant. So that means all of this hydroxide is going to react, so it's going to, all 0.004 moles is going to react, leaving behind nothing. This, because it's on the same side as the hydroxide, is going to go down by 0.004, leaving behind 0.031 moles. And because this is on the product side, it's going to go up by 0.004, leaving us with 0.054 moles. So now we can calculate, because the question asks, calculate the pH of the resulting solution. So convert these back to molarities. We still just have 100 milliliters of the sample, so to get it into molarities, it's moles per liter. So take this 0.031, divide it by 0.1 liter, divide the 0.054 by 0.1 liter, and plug it in. pH equals pKa plus log of base over acid. So the pH is what we're calculating for. pKa is still the same because we're still dealing with propanoic acid, so 4.89, plus the log of our base concentration is 0.54. Our acid concentration is 0.31. It's not 0.054 because I divided it by the volume that I had, the 0.1 liter. And you plug this nifty little calculation into your calculator, and you get that the pH is equal to 5.13. And now I have to sneeze, and I'm trying to hold it off, but I don't know how well I'm going to do. Whew, excuse me. Whoops. Okay. So now I'm going to move on to the next question as best as I can. Come on. Try to erase some of my work here. The next question that I chose for you guys is not a calculation question. It's a question that you're likely to find on a number 5 or 6 on the AP exam, where you don't have to actually do any calculations at all. So I'm just going to kind of walk you through it real quick. Make it nice and big so you can read it. Okay. Specify the properties of a buffer solution. Describe the components and the composition of effective buffer solutions. Well, a buffer solution is going to be, get the pen here, oops, an acid plus its conjugate base, or it could be a base plus its conjugate acid of some kind in there. And it's a solution that resists changes in pH when small amounts of a strong acid or a strong base are added. And the reason that it works like that is because the acid in the buffer can help neutralize whatever base is added, and the base in the buffer can help neutralize whatever acid is added. So that leads us to B. An employer is interviewing 4 applicants for a job as a lab technician and asks each of them how to prepare a buffer. And then you have 4 people. Which of these applicants has given the right procedure? Which one gets the job? Explain your answer and then explain what's wrong with the wrong procedure. So I'm just going to take each procedure and talk about them individually. So Archie, he said that he's going to mix acetic acid and sodium acetate. Well, here is our weak acid. Here's the conjugate base of that acid. Archie made an acidic buffer. So he's wrong, because they said they wanted buffer with a pH close to 9. It's doing that thing again. And so buffer with a pH close to 9 is a basic buffer. So Archie's out. Beulah mixed ammonium chloride and hydrochloric acid. Well, the ammonium chloride, chlorine is a neutral ion. The ammonium ion is weakly acidic. It's the conjugate acid of ammonia. And then, of course, you have the hydrogen ion. So Beulah just made a acidic solution that's not a buffer. And then we have Carla. Carla says she would mix the ammonium chloride and ammonia solutions. So Carla has ammonia, a weak base, and ammonium chloride, ammonium being the conjugate acid of the ammonia base. And so Carla did right, and she gets hired, because she's the only one that did it right. Then we have Dexter. Last but not least, he would mix ammonia, which is a weak base, and the sodium hydroxide. Sodium's a neutral ion, so that leaves us with hydroxide. That makes it a strong base. So he mixed a weak base with a strong base. So he did the exact opposite that Beulah did and made a basic solution that's not a buffer. Yeah, it's doing that thing again. I don't feel like writing the rest of it out. So the person who did it right was Carla, so she gets the job. Everybody else was wrong and didn't listen to their chemistry professors. Again, you notice how they put down here the Kas and Kbs for NH4? Yeah, okay, great, but you didn't have to do any math with it at all. Just use words to explain it. And use as few words as necessary to explain your answers. You don't want to ramble on and talk yourself into a wrong answer. So if you have any questions about this, you know where to find me. See y'all later.